Awesome. Thanks, Annie. Yeah, I'm not going to spend too much time talking. I really want to give enough time for our speakers, who are all experts in this field, to give their presentations. I just wanted to say a big thank you to everybody for joining today and for agreeing to be speakers in this session. So just a little bit of an agenda. We do have 9 5 to 7 minute lightning talks. I just posted a link to a Slido poll in the chat. So while the talks are happening, you can obviously use the chat within Zoom to ask questions and people can respond there. However, we will hopefully have some time for questions at the end of the session. So if you want to add questions to Slido, those questions will be upvoted by other attendees. And then based off the number of votes, we'll take the most upvoted questions at the end as a group for the speakers. Yeah, so if we have a bunch of questions at the end, I'll give a little bit of time just to equalize things, people to actually vote on questions. And yeah, so any remaining time will be used to answer those questions. And also just to plug our next session. So after the lightning talks, we'll have an hour break. And then there's going to be another cloud computing cluster session where we're going to have tutorials led by one of our speakers on OpenEO, Matthias, and then also a tutorial on Dask led by Julia Signell and her colleague. So Jacob. Yeah, so with that, I'm going to pass it off to our first speaker, Paige.
All right, thank you. Just share my screen. Oh, and now Zoom is hiding my play button. Okay. Yeah, thanks so much. Sorry, I need to figure out how I can hide my Zoom where I can't. Sorry, I cannot see everything here. Anyway, I'll forge ahead. So I want to talk today, it's probably the least technical talk, how cloud computing can enable open science. And I'm really going to talk about the part of open science that includes broadening participation in science. So I think before going forward, I just want to say kind of my own lenses through which I'll be talking today. So I'm currently at NASA TOPS, or Transform to Open Science. I also have a lot of cloud computing background. So I was a researcher at Columbia University. I've also been very involved with Pangeo, which advocates for cloud computing in the geosciences. And when I'm talking about enabling, I'm going to talk about my experience with the Coastal Ocean Environment Summer School in Nigeria and Ghana. And all of this is basically to say that this is my own personal perspective here. So this is kind of an opinion talk, and I'd be curious to, hear your own opinions and take as many grains of salt on what I'm going to say as you'd like. So I'll start with a definition of open science. So open science is the principle and practice of making research products and processes available to all while respecting diverse cultures, maintaining security and privacy, and fostering collaborations, reproducibility, and equity. So I will stress that this is a definition of open science, of which there are many. This is the definition used by the White House. It's also the definition that's used by TOPS at NASA. And it was kind of the definition created for this year, which has been deemed the year of open science by the White House. And there are 10 federal agencies, NASA included, that have kind of put open science at the forefront this year. So that's pretty exciting. And I'm just going to focus on the open science here of fostering collaborations and equity. So how great is cloud computing? I think we're all here because we think it's pretty great, maybe. So on the left here, I just have a few I've categorized some of the benefits. So the actual compute itself, we have huge computational resources that are very scalable. I'll note the speech bubbles on the right are kind of quotes from people in my science communities, where I kind of polled a few people and said, what do you think are the benefits of open science or of cloud science? So this is what they've shared. So we have data sets that can be stored on the cloud. This is really great, especially for really large data sets. It means you can access these data sets really quickly, and you can minimize copying between different institutions. We also have data proximate computing, where we're bringing our compute to the data. So we can do that very easily on the cloud. So these are a lot of great benefits of cloud computing. Now I'm going to just take a brief aside and talk about science inclusivity. So this image here is a geographic distribution of AGU publications. Not trying to call out AGU. In fact, they were the ones that had this most readily available. But I'm going to focus again on Africa, specifically West Africa. We can see that Africa is really underrepresented in this kind of international publication scene. But that doesn't mean that there isn't really amazing science being done today in Africa. There's so much. So the problem here that I see is that there's this gap, and there's a lot of great science being done, but they're just not being integrated as much into the international community. So I'm going to ask the question here, can cloud native science better integrate West Africans into the global scientific community? So I'm going to argue, yes, it can. So here are the benefits on the left again that I had before. And these lead to some really great positives for specifically West African scientists, which is what I know best. So there's no need to basically to have that huge startup cost to build your own HPC or high performance computing system. I think this is a really important one. We can debate the costs of cloud computing, but not having to have those startup funds is a really, really big benefit for scientists in West Africa, where it's hard to even get that much capital to start with. We also, with the data proximate computing, we don't need high bandwidth internet to do these incredible, analyses and access the data. And this is really huge. Bandwidth is probably the biggest limitation. Getting access to internet, they're very good at tethering phones from the, my limited experience, but they pay per megabyte. So having low bandwidth is really crucial. And it really means that they get a lot, they can really benefit from that. So cloud computing can give the access to the data and the compute resources for West Africans to do more on the computational science side. But it also will make it a lot easier for all of us to collaborate internationally. So if the tools are in place where I can just write to a Ghanaian colleague and say, hey, you want to run this code and on this new data set and see what you find, we can collaborate a lot easier if they have those tools and can access the same data and the same compute that I have available. Of course, this comes, there are many challenges that I think we're also probably well aware of for cloud native science. Again, I list a few here. So I think one of the big ones is the complex and opaque cost and permission structures. So I admit I don't understand a lot of how these work. I think we do have organizations like 2I2C that provide cloud hosted Jupyter hubs, for instance, that are helping with this kind of abstraction layer so that individual scientists don't have to deal with these complexities. But I think we can still move a bit more to break these down. We also need cloud optimized data. There's a lot of initiatives now in place. So I think this is one that we're really solving at the moment. And then the main one that I am concerned of myself is we want to make sure we avoid these cloud silos where you have to have access to the cloud that a certain institution put up to be able to access their data, but you have to go somewhere else to access someone else's data, because then we really limit our ability to collaborate with one another, to compare across data sets, and to collaborate with, for instance, our West African colleagues. So I'll just end this by saying, I think that cloud native science is an actually feasible model for training more West Africans and other represented groups into the global scientific community. But we need to make sure that we all work together as a community so that we ensure that our cloud workflows keep accessibility and inclusivity in mind. So I will end it there. Thanks.
Awesome. Thank you so much, Paige, and like perfectly timed. So that's great. Yeah, so that was a really great way to sort of motivate why we care about bringing cloud native science to the world. And with that, we're going to sort of dive into the fundamentals of cloud science with Brianna's presentation.
Yeah, thanks, Amy. I will share my screen. Okay, so today's presentation, I'm going to be giving sort of the current state of cloud native geospatial formats. For people who attended the summer ESIP, a lot of the slides are going to be similar, but we do have some exciting updates towards the end. So stay tuned. But this is just to make sure that we're all on the same page, really defining what it means to be cloud native, and understanding what's sort of going on in this ecosystem right now. So I'm going to be really wearing two hats right now. One as a data provider, right? I work at NASA, at one of the DACs based in Goddard. And as a data provider, we know that existing data collections are just growing exponentially. So this is just an example of NASA's Earth Data Archive, which is growing from 62 petabytes to over 600 petabytes by the year 2030. And just an example of the upcoming SWAT mission, we expect that to produce 20 terabytes of data every day. And that would require 20 laptops with 1 terabyte of storage. And even with 25 megabits per second download speed, that would take each laptop 4 days to just download 1 day of SWAT data. So obviously this volume of data makes it very impractical for researchers to download data if they want to do any sort of timely analysis. But my other motivation is wearing my professor hat. I also teach geospatial data analytics. And as a data user and as someone who's trying to get students involved in using geospatial data, I've seen the flip side of really high-end tech-savvy research coming out, like producing a 60-centimeter resolution land cover classification data set in Los Angeles. But none of my students could really work with this data on their average laptop. And so I want to make a point of saying that open data does not make it accessible. And that is also part of this presentation, is how do we focus on the accessibility part of data distribution. So the time, energy, resources that we need to work with this data is going to change how researchers do science. And as a data provider, this also has to change how we archive and provide the data. So I want to start with just the definition of what is cloud native geospatial, and I'm borrowing a lot of this from Chris Holmes. Cloud native geospatial are just standards and software built for the cloud from the ground up. And there are some key principles to really making a data set cloud native. First and foremost, it must be read oriented. And that means in terms of performance that it can be read both in parallel and also partial chunks, partial aspects of the data set. There has to be some level of convenience and compatibility with existing tools, and also some compression considerations for also these larger data sets that are coming out. There has to be HTTP interfaces for S3, Google Cloud Storage, Azure, hopefully open source, and being able to handle multi-scale metadata. So I'm going to briefly introduce per data type format, sort of the cloud version. And so the first one I'm going to start with is just a raster data set, right? And this is typically some snapshot in time. It's gridded data. You can think of something like a digital elevation model, but a single date multi-band file is what I'm thinking of when we're saying raster. And these currently are stored as geotiffs or TIFF files. The cloud version of that is very straightforward, a cloud optimized geotiff or COG. COGs already are adopted as an OGC standard, but there are additional restrictions to make this more performant in a cloud environment. And I'm going to explain what that is, and it's applicable to really any cloud optimized version of a data set. And that's the idea that if you have some data, right now I'm looking at just a 2D single raster file, I should be able to break this file down into chunks, and I should be able to map these chunks to this original grid data set. And what happens if I can do that is, let's say I want to just select a small portion of these original raster, I should be able to map this desired selection to the corresponding chunks from the original file. That process of chunking and storing the metadata associated with the chunks is really what makes this cloud optimized, would make access to this more user-friendly. The last part is also being able to have different scales of overviews. So you can think of having one iteration of a global map that's really zoomed out, right? And sort of as you need to zoom in closer, that's when you would have different scales of resolutions available also for extraction. Last, a true COG, and this is again true for any cloud optimized data set, is that it should be made available on a server that supports HTTP range request, right? So it's not enough to just convert a file or dump it in an S3 bucket. There has to be some support for range requests to really leverage the whole chunking and tiling features. The next format that I'm going to look at is a multi-dimensional raster. So you can think of these like data cubes, weather forecasting data, or just adding a dimension, typically in time. These files are commonly stored currently as netcdfs or HTF files. The sort of cloud equivalent of storing these types of data could be ZAR. And a ZAR is an open source specification for storing chunked, compressed, and dimensional arrays. Right? And ZAR goes beyond just geospatial data. It really is just any data that has n dimensions. But there is ongoing work to make a spec for GeoZAR, right? So we understand that we want data sets that are going to be hosted as ZARs to be compatible with existing tools, things to consider like projection, geospatial coordinates. All of that is an ongoing discussion. I highly recommend you join us. We're starting bi-weekly meetings next week, and the goal is to propose a GeoZAR spec for OGC approval by summer ESIP. The next two I'm going to just whiz by. The first is just a vector, right? So you can think of this as shape files, any sort of column type data that would include lines, polylines, strings, etc. The equivalent of that in cloud is GeoParquet, which defines how to store this vector data in Apache Parquet. Same ethos as COGS, right? There's support for filtering of chunks and sort of mapping smaller chunks of data based on column stats. You have an ability to partition the data into different files, and this enables some level of spatial indexing. Last but not least, and to be honest, my one that I least know or have experience with is just point clouds. So existing that point cloud type data sets are LiDAR measurements, right? The file formats are .ply or .xyz, where we have in some 3-dimension dot information. The COG version of that is cloud optimized point clouds. And there's a LOGZIP ubiquitous geospatial cloud format that again is helping with these chunking and faster indexing of the data itself. So a question that comes up a lot, and I touched on this again in summer ESIP, is really which format and when. And so I've heard a lot of, should we use a COG versus a ZAR? And that's really the wrong framing. I'm borrowing this from a speaker who's coming on later, Vincent. It's really use case dependent, right? So if you're trying to visualize data, you probably want COGs. If you're trying to do longer term time series analysis, you probably want a ZAR. And there is an open comparison paper that I think Vincent has been leading. But overall, there is no ideal cloud format, right? There are just different extensions of formats which allow spatially accelerated reading over HTTP, and it really depends on your use case which one you want to leverage. The last piece, which it's not a cloud-friendly format, but it's a tool to have cloud-friendly access to archival data that might not be stored in a cloud-friendly format, is Kerchunk, and I believe that's going to be the next talk coming up. I have 2 slides to just touch on topics that come up when we work in cloud environments. One of those is data provenance. And so I'm using this use case from Ryan of if we don't provide as data providers cloud-friendly data, others will. And so this is an example of a data set. It's a precipitation data set that Pangeo Forge community moved over and made accessible as a ZAR format. But they noticed a ton of errors in the data set itself. And this caused an ongoing conversation of, okay, well, who do we talk to understand these errors? Originally, they received an email from NOAA that said, well, this is a NASA data set. And then NASA responded saying, well, we actually don't curate this data set. It's an old copy. And so I just want to show this point that, Archives One are very much alive. And obviously there's a ton of effort of curation and quality control as a data provider. This is probably your worst nightmare, is somebody just copying the data and putting it somewhere else because you're not offering it in a cloud-friendly way. And you could have data provenance issues where, for example, an erroneous older version of the archive is distributed in mass to the public. The last update and kind of use case example I want to show of just more community-driven approaches of also moving data to the cloud is Pangeo Forge. So the goal of Pangeo Forge is to make it easy to extract data from traditional data repos and deposit it in cloud object storage format. And so I had first heard of Pangeo Forge from Ryan's talk in summer ESIP, and he was able to connect me to some of the developers. This is Charles Stern and also UV. And we met in Los Angeles a few weeks ago, and in about 1 week, we cranked out a sort of extension to Pangeo Forge that would leverage NASA's Common Metadata Repository tool, or CMR, where basically now you could leverage short name of data collections and move data from NASA to the cloud with just specifying like a short name and a version. So this is just, again, putting out there ideas for how to become more actively involved in the community. And my closing remarks is just, if you're distributing data, if you're using data, if you're using open source software, I really want to encourage people to get involved. I think we can really foster a new ecosystem based in reciprocity. I think especially for people working at government organizations, we're in a really good position to do this and sort of give back to the community, since we leverage and build most of our tools on open source things. So thanks, that's it.
Awesome. Yeah. And like you said, we're going to now pass it off to Peter, who's going to talk about Kerchunk. Oh, and sorry, Peter, before you start, I should have mentioned, I'm going to raise my hand if you are at time or like overtime. Is that something, Brianna, that you could see actually?
I did not see it.
Okay. Yeah, I hate interrupting people, so I was hoping I could just raise my hand, but yeah, if people could try and I guess I'll just, Peter, do you want me to interrupt you if you're running over?
Yeah, I think I'll be quite quick, but yeah.
Okay, okay, great, thanks.
Sure. So I'll, Brianna quickly mentioned Kerchunk there, and I'll just give you a quick overview of how Kerchunk works and what Kerchunk can do and how it can be useful. So the Kerchunk library provides a way to map the internal layout and chunking of various gridded scientific data files to virtual ZAR datasets. By creating standardized reference files, users can now directly access the compressed chunks of data contained in the original files as a single virtual dataset. So it's mainly raster data that this is concerning. So netcdf, grib, tiff, fits, any sort of HDF-based file, and ZAR itself. And what Kerchunk does is it creates a JSON reference file, and there's a specification for this. And Kerchunk is the tool used to create this reference file. Once the reference file has been created, the user doesn't actually need Kerchunk anymore. And it's this FSPEC reference file system that you use to create a mapper and then open it with the ZAR backend. So when you're opening a file with an X-ray, as far as X-ray is concerned, you're actually opening a ZAR file. This has a number of benefits. Obviously, it takes the older file formats and makes them cloud optimized. It consolidates the metadata and allows concurrent extraction of chunks through byte range requests. So this is possible in netcdf files and other file formats, but often requires scanning the file. And when this is spread across multiple files, it's actually quite time consuming. You can also use Kerchunk to manipulate and otherwise change the you could essentially create a virtual data set. So you can concatenate a whole number of different files together and create different views on the same data set. So this could be used to show the latest weather forecast, or perhaps considering the same weather forecast, but considering a different run. And on the user's point of view, it's just opening up a reference file and not having to worry about how the files are stored, etc. It's also minimally disruptive. I think in a lot of institutions, there's some momentum behind the older file formats, and it can be somewhat difficult to change. So Kerchunk just provides a way to do the two workflows alongside each other, and it's robust. So it's a way of sharing data without needing a custom API or anything like that. The data just needs to be on some network attached storage, whether that's S3, Open Data Cube, whatever that may be. And then in many ways, X-ray becomes the API you use to access your data. So I just have a short demonstration of what this looks like. I won't run this, already run out of time. So here we're considering the GFS weather forecast. So this is available on S3 in the native group files. I believe this is just copied across from the NOAA server. This is the full range of files. And here we're just going to extract only the group messages with height above ground. Kachunk has a number of different modules. So here, to consider group files, we use the scan group module. There's a different one for netcdf, etc. So we create a file for the, we create a reference for that. So we're just going to consider 2 files here to keep it quick. We create a reference. Kachunk will create a reference for each group message within the group. And because we're only considering one level, we can just merge these. And what's quite convenient is because the way the references are stored, it actually just becomes merging a dictionary. So this merge vars is a convenience function, but actually all it's doing is merging the 2 dictionaries because we know that it has the same coordinates. And then we concatenate the 2 files along the time dimension. And you can see here now we have a netcdf, we have a X-ray data set, and this is pointing towards the data stored on S3. So this is pointing towards the group files. And there are variables. The actual reference file itself looks like this. And for those familiar with ZAR, you'll start to pick out some of the attributes. So here's, for the time dimension, there's .z array, there's Z attributes, and the bytes considering that. And if we just list, so this is using the reference file system, we can just list what's inside that. And here I've saved that same data to a ZAR file. And if we list what looks like inside the ZAR file, you can see it's obviously following the same structure. And then just to show it, this actually provides access to the data. Here's a simple plot. Because Kachunk spits out a message for each, spits out a reference for each group message within a group file, it can actually be quite convenient to consolidate group files. So here's this another example considering the high resolution rapid refresh model, also in group. And I haven't showed how the Kachunk file is created here. But what's quite neat is this forecast. This isn't the latest one, I just haven't rerun it. But here are all the variables within an HRR forecast within an X-ray data tree. So we can see here's our, this is the adiabatic condensation level. There's all the data variables. Same with the, the atmosphere single layer surface. And you can really explore the file from within here. Essentially, your X-ray becomes your API, rather than having to, write a custom request or subset the files otherwise. That's that. We'll just move on to another example with Array 5. Here's another, this time the Kachunk file has been put inside an intake catalog. So we can just open it from the intake catalog. From the user's perspective, they aren't even aware Kachunk is being used. And here we have access to 50 years or 40 years of Array 5 data within a Jupyter notebook. And just a quick plot to show what can be done. And what's really powerful about this is that if you have a number of users using the same Kachunk file, I mean not just for Kachunk, but for any cloud native data set, this function here to consider NINO 3.4 can just be shared across users without needing to change the way it's written and interact with that, because everyone's operating on the same data set. Yeah, I think I'll just leave it off there.
Yeah, that was
perfect.
I was just gonna say that we're about at time. Perfect. Okay, cool. I'm gonna ask my question real quick, which is just, is this example available on GitHub? Is it available for you to post a link to?
Sure. If you share the slides, I've just given links to the gists of those. I'll post them in the chat now.
Great. All right, cool. I'll pass it up to Vincent.
Hey everyone. Okay, let me check my screen. All right. So slide too much. Okay, so I'm going to talk about T-Tyler and T-Tyler PG stack today. So we talk about like cloud optimized data format, and my presentation will focus on like cloud optimized raster format and how you access those formats, your data. So once you have your data in the cloud optimized way stored on the cloud, what you do with that? You want to access it, you want to access your data, you want to visualize it and to let other users use it and visualize it, for example. So Ttyra is for that. Ttyra is a suite of Python package that lets you create like web services to interact with your cloud optimized raster data store somewhere on the cloud. So Ttyra will help you create like tile service, for example, and to create dynamic tiling service. So what is dynamic tiler? So it's the difference between static tiling and dynamic tiling is like for when you want to display data, a raster data on your map. Usually you create all the map tiles that you want the client to be able to visualize. So you do a reprojection of the data, you do rescaling, data rescaling, or like apply some kind of math processing to the original data. You store all those small tiles on the cloud storage, and then the map client can access those map tiles. And with dynamic, you only keep the raster data as a cloud optimized data set stored somewhere on the cloud, and you put a tool like Ttyra in between the client, so the map client and the raster dataset. And every time the client will ask Ttyra, hey, give me a map tile of this region, and Ttyra will fetch the part of the data it needs to create the tiles and apply reprojection, rescaling, math processing, or whatever you want. Like you can tell Ttyra to do different band combination. If your raster data set has more than 3 bands, you can also change the bands if you want. You can apply like math process, like band combination, band math expression directly, dynamically. So it opens a lot of possibility for the users, and like you only get to save. You only have to have a raster cloud optimized format data set somewhere, and the Ttyra will help you to create services to display your data as the user want and not as you want the user to see it. So it really gives the power to the user to do what the user want. Like if they want to visualize like different bands or like different like band math expression on bands. So Ttyra is built on, it's a Python project. It's a fully open source and is available on GitHub. So a quick demo. I try to be quick. So I'm going to share my screen. So where is that? It's there. Okay. So a quick demo of Ttyra. So we have an endpoint Ttyra that XYZ, which is Ttyra deploy on AWS Lambda. And so we can give Ttyra some kind of open data. And for example, I'm going to use this first data set, which is a DEM. So first we get the information about the data. So it's pretty slow because I'm sharing my video and I guess my network is not good. It should work. Yeah, just fine. All right. So Ttyra gives us like the bounds. There's some info, raster info about the data. So we know that it's a float 32 data type. So knowing that it's not a byte data set or like a byte data set, we know that we have to rescale the data to create like a visual representation of the data. So, but because Ttyra is smart enough, it knows that there are some metadata within the data, within the raster data set that tells what is the maximum and minimum value of the whole raster. So Ttyra, when you ask for tiles for this kind of file, it will, it's pretty slow, I'm sorry. It will know that it has to rescale the data from the maximum to the minimum. So again, all those web map tiles that we see, the gray tiles are created dynamically, fetching only the data it needs from the raster dataset. And so, as I say, you can set options to like apply different color maps, applying different row scaling to highlight some features on your data. And so, and again, everything is done dynamically. You can apply some processing. So for example, the hill shading processing on the data. So again, every time the map client call the server will fetch only the data it needs, apply some map process to create, like, for example, the hill shading representation of your data. So that was for like a simple DAM. If you have like I was saying, like multi-bands data sets, like this one. So it's a RGB near data. So you have 4 bands. You have the red, clean, blue, plus the near infrared bands within the raster data set. You can, like T-tiler is not only for like tiles, you can also fetch the statistics like of the data. You can, there are multiple endpoints. You can build a lot of endpoints with T-tiler. So statistics, cropping, like point values if you want. And so yeah, that was just an example to get the statistic to plus the histogram of the data, for example. And as I was saying before, you can get multi-bands representation, like you can change the band representation. So here I'm just taking the 3 first bands of the data, but if I want to select like to create a band combination with the near infrared band, I just tell T-tiler that I want the near infrared band as the first band and the red and green as the other bands. So you get to see the vegetation in red using the near infrared band. And you can say use expression. So here I'm going to create the NDVI representation of the data, taking the near band and the red band, and doing some rescaling and applying some color maps on it. So again, this is done dynamically using T-tiler and fetching only the data it needs. In T-tiler, we also have, I'm sorry, I'm going fast because I have a lot of to say about that. We also support stack items. So the stack is a metadata specification to give metadata to your data sets. So usually you can put like multiple raster in a stack. In a stack items, you have like you can put a lot of things. So we try to support that in T-tiler. So for example, I'm giving a stack items to T-tiler, and T-tiler tells me what are the assets that are available. So in this stack items that I've given, there is 3 assets that I can visualize in using T-tiler. And so then I can use different endpoints to get the info about each assets, and also visualize each asset individually, or also mix the assets together. If you have like a stack items that reference multiple bands in multiple files, you can tell T-tiler that you want to merge the files all together to create like a multi-band version from one stack items. And I'll go back to the presentation. I'm sorry, I still have a couple of things to show. So what I just talked about was like using T-tiler when you have one data set, when you have one data, when you have one cloud optimizer for one stack items. What if you have like thousands, hundreds of thousands of assets of data sets? You might go, you might create a database and put all the stack metadata about those data sets. And what we did is like we created a project called T-tiler PGStack, which will connect T-tiler to your stack metadata database, and will help you to create like dynamic mosaics, or like the dynamic tiles from like virtual mosaics using all those stack metadata. And so what ttyr stack does, every time you want to create a tile for, like, let's say all your Landsat collection that you have, ttyr will ask the database what are the assets, the items that intersect with the tile, and then the database will return this info to the ttyr instance. ttyr will then fetch all the assets for each items that you want and merge them all together to create a tile representation. So if you have been playing with, like, for example, the Microsoft Planetary Computer, that's ttyr stack that powers the Microsoft Planetary Computer. So because Microsoft built everything with Stack and with PG Stack, we were able to deploy ttyr stack to create those virtual mosaics and, like, to create tiles from those stack metadata. So I'm not sure if I have still time, but I'll try.
I'm doing a terrible time at I'm doing a terrible job at keeping people on time. So we probably should move on, even though I want to make sure everybody has time. So thank you so much, Vincent. If you have more content, we'll post a link to it. Check it out. Awesome. Okay, so let's go to Kyle on Cloud Native Vector.
Hello. Can you see my screen? Hopefully. I'm cool. I'm Kyle. I'll be talking today about Cloud Native Vector data. So first, I want to just talk about what is Cloud Native, and people have discussed this a bit earlier in the session, and I think the biggest idea is that there's just too much data. There's petabytes of data in the cloud now. We can't deal with that data on our local computers, and moving the data and the bandwidth is really the hardest problem here. So we want to be able to use these petabyte scale archives without needing to download all of that onto a local machine, whether that's a local desktop that you have at home or a local computer in the cloud. You want to be able to utilize part of the data without downloading it. But the thing is that being able to use part of a data set means that you have to be able to arrange the data in that data set to group similar data together. So with a cog, you can group the pixels together and effectively create a spatial index by chunking pixels that are nearby into a similar region of the bytes of that file. But with vector, you can't always do that. So here's an image of two different vector data sets. One is points in New York City, and one is global shipping routes. Well, what's the difference here? With points, they're small compared to the scope of the data set. So each point can be binned alongside neighboring points. So you could imagine, if you have a data set like this, you can bin the points into chunks so that if you needed, say, Lower Manhattan, you could just load the points in Lower Manhattan without needing to load all of the data set. So for example, you might be able to construct a format that has an index that tells you the byte range of this exact little bin has a specific byte range that you can fetch directly from S3. But it's not always easy to do that with vector data. If you look at global shipping routes, where each line string, each feature can cross half the world, then you don't get nice small bins like you might with points and effectively with pixels. So it's really difficult to construct effective partitioning systems for vector data, or at least you can't do it in every case. And that makes it harder to construct effective cloud native vector data formats for this. So the key thing that I want to get there is that you need a lot of spatial locality to effectively be able to have vector cloud native data formats. It'll work in every case, but sometimes it'll be less efficient when you're actually trying to fetch the data, because in a case like this, if you're trying to fetch data over the East Coast of the US, that data, you might have to fetch data from like half the world in order to fetch just the data of interest that you want, because the geometries are so big compared to the scope of the entire region of data. So I want to talk about two data formats that have really implemented cloud native vector functionality. The first is flat GeoBuff, which has been around for a few years, probably 4 or 5 years now. It's a really cool format. It has this metadata at the front that has the column schema, and then this spatial index in the middle. This isn't to scale, so these left 3 sections are actually pretty small. And then that tells you the byte ranges of the features in your data set. So if you wanted data just in a specific part of New York, then you can look at the index and just load those row features. But there's also this newer data format called GeoParquet that I'm really excited about. One of the main differences between flat GeoBuff and GeoParquet is that flat GeoBuff is entirely row-based. So you have one row, which is A, and then you have the next row, which is B, where essentially each of these you could think of as a GeoJSON feature. In Parquet, instead, you have a columnar storage format. So this, you can think of like a column of an attribute, a column of another attribute, and then a column of your geometries. So instead of storing across a row, you store across a column, which has a lot of benefits, for example, in compression, because if you have similar data in a column, is most likely the same type, similar values, and compresses a lot better than data across a row. This, then GeoParquet, stores this group of columns in multiple chunks. So each one of these bins, essentially, becomes its own GeoParquet record batch, which allows you to very efficiently get all the data in a very specific region in potentially a faster way than flat GeoBuff. The most exciting thing for me about GeoParquet is that, similar to how Cog built on the huge success of GeoTIFF and TIFF before it, Parquet are already a huge ecosystem. Parquet has been around for like 10 years. There's great support in huge data lakes like Spark and other huge data systems, in tools that people are already using like Pandas, and more and more geospatial tools like GDAL and QGIS. There's support for this that builds on top of this huge ecosystem already. And so I think it's that the power of doing that, of building on the existing ecosystem, that makes GeoParquet really, really powerful. The GeoParquet spec is at this repository on GitHub. We're currently at 1.0.0 beta 1. So we'd love for people to look at the specification, tell us if you have ideas on how to improve it before we go to 1.0. Spatial indexing has been discussed, but isn't yet included in the specification. That'll probably happen after 1.0, but in a backwards compatible manner. And then I have a couple examples at these observable links that I'll put in the chat of being able to use GeoParquet to visualize really large data sets. So for example, in this observable notebook, this has an interactive visualization of 3 million points that comes to the browser as GeoParquet format, and which is essentially faster to write from GeoPandas and faster to load than really any other format for that scale. That's it. Thank you.
Awesome. Yeah, thank you so much. It's really cool stuff. And I'm excited to check out those examples. I am a little bit concerned about time, so I'm going to start cutting people off if you're running over like 8 minutes or so, so that we can have everybody has enough time to give their presentation. So I'm going to pass it off to Ryan next.
All right, great. Thanks, Amy. I'll try and let us catch up on some time. My talk is very simple. I'm going to tell you about what we've been building at our new startup called Earth Mover. I always like to start from a video like this. This is one from NASA that probably everyone has seen, the beach ball, showing all of these different sources of Earth observations. And practitioners who are trying to do really ambitious things with Earth system data today all have to confront this type of situation where they've got a bunch of different data products from different providers and, different formats. And my main point here is that users really don't care about what provider it comes from, what format it's in, really. What people want to be able to do is take large complex data sets, merge them, align them, build models, and get new insights, right? And we've made a lot of progress technologically, but I think there's still a lot more work to be done to really realize that goal. It's very important, I think, to point out, I think what everyone here knows, Earth system data is very hot right now, right? We've already seen the curve of the growth of Earth data volume from Brianna and others. We're all very familiar with this challenge posed by this exploding amount of data. I believe the user base for the data is also growing exponentially. So one indicator of that is the volume of investment in the climate tech sector, which is not all people using, Earth system data, but a big fraction of that is people working on climate adaptation mitigation work that requires really deep engagement with Earth system data. And, where is the place where government agencies, academic researchers, and companies of all shapes and sizes can all come together around data and computing? That is the cloud. That's why I believe the cloud is really central to where we're going. It's the one place big enough to hold all of this data and to accommodate all of those different diverse types of users. I'm really proud of everything this ESIP community has done to sort of move forward technology for cloud native Earth system data. My work has been mostly within the Pangeo community here. And it's just been really inspiring to see all the progress that's been made, say, in the past 5 years. Think about where we were 5 years ago and where we are today. But I still think there's a lot of unsolved challenges in terms of our overall architecture that we're using, right? So we have great open source software. And I work on Xarray. That's kind of my main hat I wear as a software developer. And there's a lot of great open source software projects out there. And then when we think about the cloud, we have a managed service that we're interacting with. And for almost everything that we've heard this morning, that managed service is Amazon S3. It's not a software. It is a service that we pay for and we interact with. And that service is basically just a key value store. It's just, we tell it what key to store our bytes at, and then it gives us our bytes back. And its great feature is that it's extremely scalable, extremely stable and robust. But it knows nothing about what you put in it. It couldn't care less what's in those bytes, right? Now, in between our open source software and that service are a ton of difficult engineering questions. A lot of head scratching about, well, what file format should we use? How do we know what data we have in S3? S3 is not really a very good database. How do we expose that information to users? What kind of catalog should we use? And then if we're not just doing totally open and public data, but perhaps have restrictions or access controls, how do we monitor and control that access? And what I see happening in our space to solve these questions is a lot of really great, but ultimately really bespoke engineering and integration efforts. I'm looking at you, NASA, all the amazing systems that are getting built just for NASA, just for this DAC or that DAC, or just pick on NASA because they're big and I know people there. But everyone's doing this, right? There's a lot of custom engineering happening in this layer between end users and the managed service to solve this problem. So what we want to do in EarthMover is create a new managed service that's going to solve some of these challenges around data integration that really enable people to build data lakes for Earth system data much more quickly. A service that sits on top of object storage that still interoperates with our open source ecosystem, but solves some of these problems in a generic way, right? And so who is this? This is what we call Array Lake. It is a data lake platform for scientific data. who do we imagine using this? Well, I think a lot of folks here would identify as a data manager or data engineer. So you're really one of our main personas we're thinking about here. People need, I think, a place to put their data into that is a little bit more understanding of what that data actually is than raw S3 as a key value store. We think that this can be really valuable to scientists and researchers as a place to come and do data science and analytics. Machine learning is a big part of this landscape now, right? So we need a place to put derived data sets that are being used to develop and train and run inference from machine learning models. And we want to create a layer of technology that people can build on top of to build new systems, products, data-driven software in the cloud. And then finally, we also want to solve some of these challenges around the governance of data, right? How much data do we have? Who can see it? How much does it all cost, et cetera, right? So some of the features that we are building are on here on the screen. We're really first and foremost thinking about trying to solve this data catalog problem. Stack is a wonderful API for data catalog access as a client, but it doesn't necessarily tell you how you're going to update the catalog, how you're going to edit the metadata. So we think a deeper layer of technology is needed besides just a standard to query. We're really excited about everything that we've learned through Kerchunk and ZAR about how all of these file formats are essentially the same under the hood. GRIB, ZAR, NetCDF, HDF, GeoTIFF, just a bunch of chunks and metadata, right? And so we think that can kind of be generalized over and users can not have to worry so much about what file format they have. Version control is a really important part of this story, right? So when you're maintaining a dynamic archive of data, it's really important to be able to have, ACID transactions, atomic commits and updates to your data, ability to travel in time across different versions. There's huge potential for data virtualization. I think Kerchunk has demonstrated that, right? We can create data sets that don't exist on disk and provide them to users, and users don't really have to know about that. Data governance is really hard and really hard, I think, to solve just at the software layer. But most companies who are working with data, environmental system data in the cloud have, strong concerns about data access controls. They only want their team to be able to see it. They want to be able to know who's seen their data, et cetera. And then the thing I'm most excited about is also the farthest away. But I think with this layer of technology that Array Lake provides, I think we can get deep into query optimization. We can make things like rechunking, regridding, recompression, all happen automatically in the background, and we can couple that to our clients, which are querying that data to really massively supercharge performance on things like time series analysis, or composites, or any of the many varied visualization and analysis tasks that people have to do. We are looking for people who are interested in these problems, who might be interested in taking this for a test drive. That's kind of why I'm here today. So if this sounds like something that could solve some problems that you or your organization is facing, please reach out to us.
Awesome. Thanks so much, Ryan. So let's keep moving on to Matthias on OpenEO.
Yes, thank you, Amy. So I'm going to talk about OpenEO, interoperable geoprocessing in the cloud. And I would like to start with a question, basically. So how do we process EO data in the cloud right now? And what we often see is this, right? You have a couple of clients and each of them needs to communicate with a different service like Planetary Computer, Google Earth Engine, or whatever you have. And this means you need to learn different kinds of languages or clients or programming languages, whatever this specific service offers. And I would like to give an example, like just on Monday, there was a podcast episode on a podcast called Minds on Maps. And they wanted to do a comparison between the different cloud services like Planetary Computer, Google Earth Engine, and do the same use case on flood mapping also in QGIS, basically. So they invited 3 experts, each for this different like processing platforms, basically. And in the end, they didn't have a domain expert necessarily in the round, just experts on these platforms. And the results they got were all very different workflows, basically, because they needed to be adopted to the individual platforms they're working with. And the results also looked different in the end. They were only comparable by numbers, like how many pixels were actually flooded. And that's something we would like to solve in OpenEO, which results in something like that, where each of the clients, maybe R, JavaScript, Python, or whatever, can speak the languages of all of this, like something like a GDAL for the cloud, basically. And for this, we have specified and developed a solution named OpenEO, which consists of, first of all, an API. That's the grammar of the language, basically, and processes, which is basically the dictionary. So it's basically just like we talk all here in English. That's the language you should or can then talk to the cloud providers, basically. This API and processes can actually make your interoperable process chains possible, so that you have one process chain and you can use them on different service providers and get results for them. This is all centered around data cubes, so that you don't really need to look into the details of like how are my, I don't know, tiles or individual scenes are structured. How can I combine them to look at a larger scale? That's all taken away from the user. You don't need to take care about file formats, etc. It's all data cubes. You just work with the data in a single way. And you have different implementations then, right? You would have, right now we have implementations for like 8 or 9 different providers and different software stacks. You see examples here on the right: Google Earth Engine, GeoTrellis, Dask, Xarray, Sentinel Hub, etc. And if you then run this interoperable process chain on these cloud-based data processing platforms, in the end, the aim is to get comparable results, so that you just take your single script or process graph that you have and send it to all these backends and look at the results and see how they're different. That doesn't always work right from the beginning. You see here, we did that right at the beginning, and you can see that they are very similar, but depending on how your initial data is and other parts of the like backend infrastructure, it might be a bit different, but in the end, you can at least see what's different and maybe mitigate these issues in the end. Then this is all provided with a rich ecosystem now. We have client libraries for Python, JavaScript, and R, so that you can use your known tools, like you can run this in a Jupyter Lab environment or in RStudio, or with JavaScript, of course, you can make fancy web apps, etc., which we also did. So we have now a nice visual tool for not so advanced users, maybe for more novice users that are more into like really domain experts that don't know maybe programming so well. They can just use the model builder in the end, click it in the browser and just get results visualized there. This is all built around cloud native, the cloud native ecosystem basically that we have. It's built on top mostly of Open Geospatial Consortium APIs. It uses Stack in the background for ingesting data, for exporting the data again, so you can all the results you can reuse again with the Stack ecosystem. It exports COG mostly right now, but you can also like in the future do whatever you want with other file formats like GeoParquet coming up, for example, for vector data. And it's all open. So that's all developed initially under the European Commission umbrella. we're now opening or it was always open for anyone, but it was always viewed a bit of like an EU thing. So it's now going to be, it's completely free. It's on GitHub. You can interact with it. It's all licensed under Apache 2 license. The backends are available open source. The clients are available open source, and the specifications as well. So this is now a proposal for the EO community, basically, to implement this, make proxies for your infrastructures, so that people just need to learn and know a language, and then can interact with all the different processing capabilities that we have and should use, so that you don't need to look into all the details anymore, and just really get to the work and get answers for our questions, basically. So that's my talk. Thank you. And
awesome. Yeah, thank you so much, Matthias. Do you want to plug the tutorial on this later on? Do you want to?
Oh yeah, indeed. We'll give a tutorial, Benjamin and me, on OpenEO first of all, and then on OpenEO platform, which is a federated infrastructure here in Europe, on top of OpenEO. Where multiple backends are connected, so that we even make it more easier to make this data available from a single source, and users don't need to care about like, where do I need to connect to? Do I need to use Google Earth and Planetary Computer or whatever? So feel free to join that. We'll show a bit how this works, all more in detail. That's at I only know the time in my time zone, so that's not very helpful.
Yeah,
in an hour or so.
An hour after this finishes, so in about whatever that is, 80 minutes. Awesome, cool. So let's go to Sam for our second to last talk.
Thank you. Great talk, by the way, guys. Let me know if people can see my screen.
Yep.
So I really love the setup that everyone did today morning, because people were talking about the fact that there is a limitation on bandwidth of data that's available. And the one thing I always focus on was the fact that access isn't equal to accessibility, right? Just because I put my data somewhere doesn't necessarily mean that someone will be able to actually interact with the data, will be able to do anything with the data. Just to give a little bit of background about myself, I'm basically working for my data job as Planet Lab. I'm a solutions architect there, but most of the work that I'm going to show here is not related in any way to my main work. It's mostly the work that I do as a Google developer expert and a community advocate. I work with the Google Earth Engine platform, and I've been working with them for a couple of years. And I'm here to talk about the Google Earth Engine community catalog. So for a few of you who might have been using the Earth Engine catalog or Earth Engine itself, it's a cloud-native remote sensing analysis platform. The backend catalog has about 80 petabytes of data that includes mostly open source or openly accessible data that have been made under different licenses and made available to users. As Matthias said, there's also a stack catalog for that, and you can actually access those through OpenEO and through other platforms as well. So this was well and great, but one of the issues that the Earth Engine catalog had, or one of the things that we really found out, was there wasn't really a data common. There wasn't really a way for people to actually contribute their own data that was being produced by research papers, data that people were writing like amazing papers on, but they were putting it in stores like Dryad or Zenodo and Figshare. And while all of those are well and good, if you really think about the FAIR principle, there would be a lot of data transformation that would need to be done to actually bring it and make it like repeatable in the same way in which probably the authors wanted it to be. So one of my friends, actually, Erin, reached out to me. She's a professor at University of Alaska, reached out to me and said, hey, would you like to make these data sets? I'm really having trouble kind of getting these data sets available in Earth Engine. Can you actually fetch those for me? And that's where the idea was born. And I said, why just make it available for you? Why not make it available for everybody? So we basically created a community, the Google Earth Engine catalog called the Earth Engine Community Catalog. And you can go to the website, by the way. I also pasted, hopefully, the link. If not, you can just follow that link. These are for data sets that are often unavailable for direct use in Google Earth Engine. These are your research catalog papers, but these can also include globally accessible data sets. For example, it has data sets like Facebook's HRSL data, the high resolution settlement layer. It has Microsoft generated building footprint layer. Microsoft generated like layers such as the road network that they just released. It has ESA's land cover network and so on. And it's basically updated every so often. So every week there's a new update that's posted. As of now, I've been running this project for about 2 years, and I've been able to process about 1,116 data sets, totaling about 112 terabytes. The entire catalog is hosted on Google Earth Engine, which means anyone who is on Google Earth Engine will be able to just sign up for Google Earth Engine and utilize these data sets, keeping in mind that there is attribution. So just make sure that you attribute the people whose data sets you're using. That's just general good practice that we hope. There is billions in feature collections and image collections. This does not reflect the overall number because some of the feature collections are in nested folders, and I've not actually gone in and queried all of the nested folders. For just to give you all an example, the building footprint itself is over 1 billion plus data sets. So I'm just going to switch over to a live demo right now. I already have this open, so I'm just going to hide my floating panel. Okay. So this is the community catalog. The community catalog is basically has a setup where you can come in and you can interact and go towards any single data set. So for example, ORNL generates the Landscan data set, and they just made it open source, I believe, a couple of years ago. I came in, I ingested the data set, and I made it available on Google Earth Engine. And what this also provides to the user is not just a way in which they are, they can request the data set, but this will also give you example folders, and example scripts. So you can come in and get an entire folder that you can add to your Earth Engine collection right now. So it will appear in your readers list. And you can actually go in and say, hey, okay, I want to add this Landscan data set and I want to see like what's actually available to me. I can go in and launch like a CMIP futures data set, for example, and I can run this really quickly. So a lot of these things are actually available. Here's a good example of the latest data set that I added from Canada, which is the HRDEM, it's DM and DTM, so you can actually get a really cool difference layer if you wanted to, and you can interact with it and you can play around with it in Google Earth Engine. This is completely community focused, and the idea is that basically people will be able to contribute their data sets. So the way in which they are contributing right now is you can go in and you can create these tickets when you go into the issues tab and click on new issues. Sorry, mine is not logged on, so I'm just going to go into my slides because I actually have an image of this. So you can actually bring your own data sets, you can report a bug, you can suggest examples for this, and you can interact with the catalog as you deem fit. Also, updates to the data set are made weekly, like I said. So if there is any data set that has a newer version, there are crawlers that I built that'll go and fetch these newer data sets from Zenodo, from Figshare, from Dyad. But if an author wants to update the data set, they can also directly create a bug and they can actually report that to us. So this, we hope, is a community asset that remains for the community and builds on top of what they would like to see from their own data sets. And we hope that it's filling a gap that's currently available in terms of making research data sets more accessible and also reusable, right? Like, we don't want people to make multiple copies of the same data. If there is an easy platform or place where you can use all of this data, this gives us a more direct way of saying plug and play in the truest sense. So thank you so much and have a visit. Let me know if you have questions. I'm happy to talk about it. Thanks.
Awesome. It's really amazing work, Sam. Super inspiring. Let's go to our last speaker, who is Anne Foyo. Thank you, Anne.
Okay, let me share my screen. So hopefully you can see my screen. Oops, sorry. Yeah, so I will talk about a Row Hub, a research object hub, and the goal is to be able to manage and preserve your research work, make it accessible and available to everyone, and to be able to discover new knowledge. So I will first start with some motivation, and the initial motivation was as a climate scientist, I usually want to find and access existing work, but a scientific paper are usually not so useful to me. I mean, they are useful, But if I can't find, for instance, Code or Jupyter Notebook I can reuse immediately, it speeds up considerably my work. And this is the same probably for most people. And the thing is, when you found a Jupyter Notebook, the first thing you want to make sure is it is reproducible. So you can reproduce what has been done. And this is the first step. You need to know what computational environment you need, maybe how much resources you need, RAM, CPUs, etc. But usually what you want to do is to reuse it, for instance, with different data, and you want maybe to collaborate with a large other collaborators and change here, for instance, the Jupyter Notebook. And eventually you want to publish the new finding. But the most important things, you would like everyone that has initially contributed to the work to be rewarded. Because if you only have the final paper and the final Jupyter Notebook or the final work, you forget everyone. So in terms of provenance, and this is not only the data provenance, but this is also software provenance or anything that has been part of the research work. So here on the right-hand side, you see what you see when you publish on RoHub, which is this research object repository. So a research object will have like a title, it will have a short description, a sketch, and we try to organize the data in such a way that it is reusable, and reusable is something not so easy. So we want to have, for instance, different folders for the inputs, for the outputs, maybe for the tools, etc. We want to also to have metadata, because if you are not from the discipline, this is very hard to find something useful to use. So we have a text mining service, and this is super helpful for discovering a new research object and a new, for instance, Jupyter Notebook or other resources. Let me summarize what is a research object in a nutshell. You can see a research object of like an aggregation of different resources, and this is something that will evolve as you work in a project. So initially you have some ideas, then maybe you start to have some data, maybe you have the bibliography, maybe you make some presentation, and then you have software, model, workflows, and maybe services. So everything will evolve, and at some point you can make snapshots like we do for releases in GitHub. And regularly, you can show what you have achieved at a certain point in your research. So research object is represented as a raw crate, which is a community-driven standard. And what you can find in RoHub is a registry of research object that you can access and register freely using, for instance, your ORCID identifier. And eventually you can get a digital object identifier for each of the snapshot or when you archive a research object, but it always has a persistent identifier that you can share and you can invite collaborators. If you want to know more, you can, for instance, see what we have written in the Turing way. So here, this is an example of a research object that we can find. So here, this is, as I showed before, it has a title, it has a description, some metadata, but most importantly, you can link resources to each other. So typically, if you have a Jupyter Notebook, we know it has some requirement, which can be the computational resources, but we could also link to a service, but we can also link to some resources, how much RAM you need, how much CPUs you need, what kind of resources you need. So for instance, here, if I click on input data, I can open it, for instance, here on the Adam platform, which is a data cube service. And when I open it on a data cube service, even if I don't know anything about the data, I can visualize the data and I can browse the data. So I can go back and forth in time. I can maybe zoom on a geographical area. So if you are not from the discipline, it gives you an insight on the data before you start even using the data itself. And you can do the same for tools, for instance, for Jupyter Notebook. I mean, this is fairly easy, for instance, to associate a Jupyter Notebook with a requirement file, and for instance, to open it in a resource such as PyBinder or here a GI Notebook. This is very similar. One thing we realized is it's really nice to have, for instance, Jupyter Notebook, but a Jupyter Notebook is hardly reusable and changeable if this is not well organized, because it can be very messy. So this is what we call like community of practice. And it's really important to have like some kind of structure, but an agreement within the community how we could organize, for instance, a Jupyter notebook to ease reusability. So for instance, to have a title, maybe to have some context, to separate the data, fetching from the data analysis and visualization, make sure everyone cite, and we want to cite everything, not only like the scientific paper, but also software developers and packages that have been used in the Jupyter notebook. And there is a light collaborative review. So for this, we have teamed up with the Environmental Data Science book. So it's an initiative led by Alejandro Coca Castro. He's working at the Alan Turing Institute. And the idea is really to think about all together how we can develop best practices to increase the reusability of research work. And if we follow this path, it's much easier, for instance, to reuse different research objects or different Jupyter notebook and to combine them and work on a different aspect of the science. So for instance, here, what I have done, I'm more an atmospheric scientist, so I can work, for instance, on the impact of COVID-19 lockdown on air quality, but I know nothing about water. So what I have done, I have teamed up with someone else working on water quality. And this is something that the text mining service can help me to find other research objects and other scientists working on this topic. And then we work together. So we created like a new Jupyter notebook that that others also can reuse. There is a more comprehensive demo if you are interested. And otherwise I will stop here and thank you for your attention.
Awesome. Cool. Thank you so much. Any immediate questions? Since you went last, you get the benefit of, I'm going to open it up for questions for Anne if anybody has burning questions or questions at the top of their head. Feel free to just speak up or raise your hand and I can call on you.
There, Amy. I just dropped a question for Anne in the chat there. With respect to this idea for having sort of a standardized community kind of thing, have you thought about positioning this as something that you can invite people to submit and publish, get a DOI, get some sort of recognition for that notebook as a first class submission of things? Having a common look and feel sounds like a really good idea. We're doing a little bit of that through an AGU-led project called Notebooks Now, but it sounds like there's some overlap there that you may want to connect on.
Yes, definitely. I think I mean, the little I know about notebooks now is it looks very similar. I don't think they have agreed on the technology yet, but definitely I think to have an overlap. Thanks.
I'm gonna ask the speakers real quickly. Is anybody going to have to drop right at the bottom of this hour, so that we can ask questions of those speakers before they have to leave? Okay, cool. So what I think we should do now is, assuming that we can stay on for, I'd say like 15 minutes after, like, I'd say, 9:45, 12:45 p.m. Eastern, I'm posting a link to the Slido poll. There's already some questions in there that people have put in and voted on. And I've also jotted down a couple of questions in our slide deck, so I'll put those in here too. So for the next, I'd say 2 minutes, I'm going to ask people to put in any additional questions or upvote the questions that are in the poll already. I should have planned for some like do 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 do. Okay. All right. Cool. Well, we have a bunch of people who have upvoted this top question, so let's start there. Researchers at agencies, here, let me share my screen actually, so you guys can all read along. Okay, so you guys can see the Slido poll?
Yes.
Cool. Sweet. So researchers at agencies are not responsible for setting cloud policies. How do we get the right people to the table to help avoid cloud silos?
Is this for anyone or?
Yes, anyone here.
Yeah, I'm sure that the agency people will have great thoughts in this, but I do want to say that this is exactly the thought that I've had when I'm thinking about the fact that there are large amount of data set agreements, for example, NASA with AWS, and a multi-cloud policy does not exist right now, right, for a lot of the agencies. So I don't know if there's a solution apart from the fact that if there is data behind authentication and agencies don't care about egress, which they do, then it would be fun. And it should be basically possible for anyone to just plug and play the data no matter what cloud it lives in.
Cool. I think I saw Ryan's hand go up next.
Yeah, I don't have a direct answer to this question, but I will state some insights I've gotten into it from this new perspective of actually, trying to sell something to people, which is I think a useful exercise to understand this landscape better. We're in a situation, a lot of people are in a situation where they have no voice over what like enterprise services their institution buys, right? So like me as when I was a university professor, right? Like I had really no say, like my university decided like, we'll buy like, Zoom and like, Globus and like Microsoft Word, like, and there's like zero feedback loop for me as like a user of the tools to like have any say in like whether those things are good for me, like whether they meet my needs, whether I like those products. Like it's made in some like very far away office of my institution. And I imagine it's the same way at a big place like NOAA or, ESA or whatever. Like it just, the practitioners just have no voice. It's a very different scenario when you're talking to like a small, startup, right? Where like there's just like a dozen people, and like if the tool is working for them, they'll like dive right in and they're happy to pay. And if it's not, they're just gonna like cancel or or like give really good feedback or whatever. And so like I think the key question is like, how do we enable some of those feedback loops where the people who have to use the tools and products somehow get to like have a voice in like how the institution deploys its infrastructure money? I don't know the answer to that, but I would like someone from NASA or one of these agencies with any insights to respond.
Yeah, we'll go to Paige, and then if somebody from NASA wants to respond again.
Well, I am now at NASA.
You are at NASA.
But I am new. I'm new to NASA, so I don't have much to say. But I think that is a really great perspective, Ryan. And these are very much my personal thoughts right now. I'm very new to NASA, so I'm not speaking for them by any means. I do feel like it is interesting that now I may have a voice. I'm working on the admin side of science, trying to help enable open science. And it is interesting, this discussions of, oh, we need to figure out what the community wants. And then they put out surveys and things like that. It would be nice to see some better ways of engaging. And maybe that means, I'm going to try and do my best. I feel like I'm part of this community, and I'll, try and raise my voice when I can. But anyway, very open to hearing other perspectives from anyone here about what I and my team could do better. But I think it's more than just, an institution's community talking to their institution. We need to make sure that the institutions are talking with each other as well. So there's a lot of lines of communication that we need to enable. And I think these are just some of the hardest questions in kind of open science, is how can we best communicate and not duplicate efforts? And, we see all these great things going up, like I said, all these silos, and it's, yeah, I don't have a good answer, but I am hoping that, maybe from the inside, I can start to better understand NASA's goals. And then maybe we can talk to some of the other agencies, some of the other universities, and not just in the US either, but internationally, which I think is another real challenge when you're working at a US agency, which has its own priorities. So somehow we have to make sure we align our priorities. And that's much easier said than done. So I don't really have any answers either, but would love to hear others' thoughts.
Eli, did you want to?
Yeah, I can kind of talk about that in sort of how we, so I'm a research scientist at NOAA Fisheries, and we've definitely kind of dealt with that issue that I didn't actually catch the name who mentioned that, in an academic situation where the end user is not consulted on what tools are purchased. And definitely, like, every government agency, you're a scientist, you have run into this where you feel like you're just sort of fighting the bureaucracy, especially if you're trying to do anything with IT and with cloud. And so for us, we're dealing with an issue with this. It's not actually about cloud, but it's really totally related. It's actually about GitHub Enterprise.
GitHub is cloud. GitHub is cloud. It's like a cloud service. Like, that's a great example. It's not AWS, but it's cloud.
Yeah. So the process for us was, first off, starting to get developing connections across our agency. So we're divided, NOAA Fisheries, we're divided into like these 6 different big science centers, and we have no communication across. So the first step was just getting the connections, being able, and this was with workshops and trainings, and starting to get the connections, and then identifying the quote unquote bright spots, the people who are really invested in trying to make change. And then the next part was just by going to talks, talking with leadership, making the personal connection. Somebody says, hey, you know what? I think that person would help you. Go talk with them, which is kind of terrifying, but you just have to go on luck. You happen to be in the room with that person and you introduce yourself to them. And that's how it started. We made the connection, found those people in our leadership, and then somebody in leadership on the science side was willing to begin spearheading our talks with our agency, IT and cybersecurity. And yeah, it was hard, but being really dedicated to having open discussions. We weren't going to be quiet. We had to say, what you're doing is preventing us from doing our work. We cannot do what we need to do. We're in a situation, climate change is on us, big data is on us. We are going to have to adapt really fast. And what you are doing is stopping us from adapting. We need a new way of work. We have to be at the table to make these discussions. You can't tell us how to manage our work. We're professionals. We know what we need. We need to collaborate with you, but you need to listen to us. If we say what you're doing is not working, you need to listen to us and believe us, and we need to come up with new solutions. So it's really hard. It's all about developing trust with people, community building, and having those discussions. So it's hard work, but we are making a lot of progress.
Yeah, it's really important passion to hear, so I appreciate that. And then Annie, I saw you had your hand. I see Alexi and Annie both have your hand raised. Annie, is there something, do you have a question, or is it about the meeting itself?
No, I actually have a question or a comment.
Okay.
So,
all right, so let's go to Alexi.
Tactical thing.
Let's go to Alexi then.
Yeah, I mean, I would say that, like, it's hard to underestimate, or it's hard to overestimate just like the level of bureaucracy that we have to fight to sort of do anything, even at like relatively quote unquote forward-looking organizations like NASA. So I mentioned, the PCAR thing in the chat. I mean, like, there's a McCain Act, which means anything with China is on automatic no, which means that every single thing has to be screened for any kind of affiliation with China, right? That's just like one tiny example. We went through a process at Goddard where like every single PCAR purchase we had flowed through like 3 people, right? So you have a 15,000 person organization with all purchases flowing through 3 people. You can understand how that's kind of a procurement bottleneck, but this is the kind of thing that happens in governments. And even the procedures that we have for like revising our procedures are themselves deeply bureaucratic, right? So at NASA, to like revise our software release policy, we have to get like written consensus from all of the different organizations, even within NASA, like the different NASA centers, each have to meet with their leadership. The IT security people have to meet with the general counsel, which has to meet with everybody else. And so I think that one of the deep frustrations that I have is that this makes it extremely hard for us to respond in a really nimble fashion as an institution to a rapidly evolving technological space, right? Like by the time we have like formally in the government way, like evaluated technology, it's, you know, by that point, it's already like out of date, the community has moved on to something else. And so I think sort of there's the bureaucratic piece of this, and then there's just like the, you know, the sheer scale of like NASA's Earth Science Data Enterprise is also really hard, right? We're not talking about a small number of large gridded data sets. We are talking about, what is it at the latest count, between 10 and 15,000, you know, with a huge long tail, highly diverse data sets, you know, which boil down to, you know, also airborne campaigns, all kinds of satellites. And so with a bunch of engineers from a bunch of different institutions working on those. So I think that that's, you know, that's all hard, and we're sort of doing our best. But I think this is where I think really the way forward for NASA is to sort of like identify what are the sort of external partners, you know, whether, you know, organizations or other kind of groups that we can work with to sort of spearhead a lot of that development. And then we sort of selectively ingest that into our own workflows. To me, that seems like a potentially better model. But this is very much my own opinion. I'd be curious if some of the sort of people that have been at the DAX longer or at this longer agree.
Great, thank you, Alexi. Annie?
Yeah, just really quickly, wanted to share that one thing in terms of understanding user or researcher needs within agencies. So last year, I had a thing called the NOAA Cloud Pathfinders program, where people within NOAA researchers got to experiment with cloud computing using ESIPs, basically allowing them to access AWS credits through ESIP. And what that enabled was those researchers being able to have conversations with leadership about what they could need. So it was kind of allowing them access to a really open cloud environment. But what that did was then they could talk to their offices about the value of cloud computing, what they were able to accomplish, what services within AWS they were needed. So basically just like a prototyping and a place to experiment with a technology that they couldn't have that unfettered access through NOAA, but then they could have conversations with leadership about the value of cloud computing, about what they were needed, about what they could do, and share those experiences. And so it was just an interesting exercise in allowing researchers to try a service that they didn't have access to, and then allowing them to have more informed conversations and advocate for themselves for leadership because they were able to experiment. So just wanted to share that.
Yeah, it's a great program. Rich?
Oh, yeah. Yeah. I was just following on Annie's comments there. You know, one bright spot may be that, you know, all agencies don't need to get on together. Like if one agency leads the way and, you know, other agencies are like, oh, that agency is doing it, then maybe we should do it. Because, you know, that's exactly what happened with the Cloud Pathfinder. You know, I started showing that around USGS and people are like, well, why is that only happening for NOAA? Let's get on board with that. So, you know, just some agency has to do it. And then, you know, the other agencies will want to do it too. It's cool.
Nice. Sounds like that would be a good showcase then to do Pathfinders showcase at some point, maybe for both ESIP and Pangeo. Cool. Paige, did you have another comment?
I did. I'll be quick because I know I talked before. I think one thought that I didn't mention before that has been interesting in some of the people talking now is like dialogue between like the scientists, researchers, and leadership. And I think this is an interesting distinction that leadership is separate from them. And this is actually something that Ryan Abernathy, I was his postdoc until very recently, and he gave me very good advice of don't get too far away from the actual research and science itself. So I actually wonder if, you know, we could think about what we like, who are the leaders, like in leadership roles, in admin roles in our science institutions and agencies, and should we kind of rewrite these roles? Because so often they really take you and remove you from the research, and then it's been maybe a few years since you've actually done any research, which makes it really hard to, you know, keep up with this ever-evolving landscape of tools and needs. So this isn't really something I think any of us can solve, but I really wonder if we should be redefining what a leadership role is. Maybe it's a part-time leadership role that includes part-time research, or, you know, I'm just spitballing here, but I thought it's an interesting way that we're saying leadership is separate from the community. They should be combined as much as we can, and then that will help with that communication barrier.
Yeah, I'm sort of virtually looking at Alexi right now. I feel like he's trying to play that role right now, and it's probably just a lot of work and really stressful. So I don't know if you want to say anything about that, Alexi.
Yeah, I mean, one of the ways that I try to do what I do is by completely abandoning all of my science research, right? And so in abandoning that, I can almost start to maybe keep up with like a fraction of the work that is required to sort of to put pieces together. I mean, I think that to me, like one of the insights I come back to over and over again is like the Kurt Vonnegut thing, where it's much easier, it's much more fun to build than to do maintenance, or whatever. I'm paraphrasing here. And I think there's like, it's hard to smash systems together and get them to work together with each other, and much more fun and rewarding. And in many cases, we're incentivized to sort of carve out individual new silos and say, look at this new thing I built, right? Rather, you know, that's like, cool, that's rewarding. That's like a presentation you can give, look at this new thing, right? Whereas saying like, oh, I made this tiny tweak to this one system and now it works with this other system, and it took me twice as long to do it because I had to understand both systems. I think that's really hard. And it's not always rewarded. It doesn't feel rewarding necessarily. But I think ultimately that's one of the ways that we can get away from some of this fragmentation. And, you know, and part of the other, you know, again, going back to sort of interagency stuff, you know, there's places where like you need, for various reasons, to have people that are 3 orders of magnitude above your pay grade to agree that it's even worth connecting these two interagency kind of things together before you are even allowed to try to connect some of these systems at sort of a software, you know, or data pipeline level. So I don't know. I mean, as far as like changing bureaucracy, my experience is like the way that it's most effective is when you can specifically identify specific bottlenecks and provide very specific recommendations for change. But doing that itself requires just a ton of work. You know, you have to read all of the relevant like policy guidelines. You have to read what other agencies have done to get a sense of like if everyone agrees or if there's some differences, and then sort of make specific changes that you recommend to very specific people. And only then does the change actually happen. But again, somebody needs to do that, and it's sort of painful work. Again, work that's not necessarily rewarded. So
yeah. I hope that this cluster and ESIP overall can be a space to start to generate some ideas around this and make progress on it. Obviously, we're not NASA or NOAA governance, but if we can start to share ideas on how to make it more possible, it can be a meaningful place to make progress. Unless there's any other thoughts on this, I'm going to move on to the third most upvoted question, because it's targeted at Vincent's presentation, and since he's here, it might be good to give him a chance to speak to it. So yeah, Vincent, I've always struggled to understand when a server-side process like ttiler is needed versus when cogs plus in-browser transformation are sufficient. Do you have thoughts about that?
Yeah, sure. So if the in-browser transformation are sufficient, yeah, ttiler is useless. You don't need to use ttiler if you have a web client that is able to fetch the code directly and do transformation in the web client. But then you have to understand that if you fetch the code directly from the web client, you are also going to transfer a lot of data like directly. If you are going to use the whole data, that's fine. But if you only need like a visual representation of the DEM, you don't need to download the data as a float 32 data type. You only need bytes data. So using T-Tiler can reduce the amount of data transfer that you do just for visualization. But if you want to have if you have the capabilities in the web client to do everything, that's fine. And if you don't worry too much about like data transfer, that's also fine to not use T-Tiler. But T-Tiler can be a proxy to reduce the amount of transfer that you allow in the web client. And also T-Tiler can enable other things that you cannot or you don't want to do in the browser, like mosaicing. If you want to mosaic multiple data together, like doing T-Tiler PG stack, for example. So you don't want to fetch all those raster and like mosaic them together. You do those operations as close to the data so you reduce the time so that you spend processing or downloading the data, and you only download like the visual representation of the results.
Nice. Did anybody have any follow-up questions, or does that answer the question of whoever posed it? Yeah, that was helpful. I should have prefaced that by like, we're making a dramatic shift from like high level governance discussion to like very technical answers. But yeah, that was great. So thank you, Vincent. Okay, so our second most upvoted question, I'm going to jump back to that one with our sort of remaining overtime. I feel like this is like a soccer match. I keep adding extra minutes. Federated data access. There are different approaches. Data lakes, such as Array Lake, which we just got a presentation from Ryan about Array Lake. So these data lake approaches where you have many different disparate heterogeneous data types versus data cubes, which usually you have some pre-processing done on the data to put it in these compliant data cubes. And then you can put something really cool like OpenEO APIs on top of it. So when does each make sense? Do people have thoughts about that?
Can I just offer like a slight clarification about what I think is being asked like here? I asked like a similar question, then I withdrew it because it was so close to this one. But like, first of all, I want to like contrast like, so I don't think it's necessary between data lake versus data cube. Like I'm not sure that's how I think about it. It's like it's a question of like what an architectural pattern for data analysis. Like, so when we're accessing data like directly on S3, whether it's Cogs or ZAR or GeoParquet or whatever, and like you're just connecting directly to the data with whatever client you want and processing. That's what I consider like a data lake style approach. So like S3 is a data lake. That's like literally how it's marketed, right? Whereas like I see OpenEO or Google Earth Engine or something like that, it's pushing more specialized compute to the server side, and then you're interacting with that through an API. So like that's how I tend to break these down. Like you can do data cube analytics either way. Like a data cube to me is really more about like a data set that has been processed and harmonized somehow, and less about like the specific architecture. And I'll just stop there. I won't really give my opinion on the actual question.
Yeah, I don't know, Matthias, do you have any thoughts about this question?
Yeah, so I mean, OpenEO, you basically built on top of a data lake. So if you need the raw data and want to be completely free, you probably want that data lake. But if you want something on top, want to have it more easier because it's like already made part of a data cube, you use OpenEO, and it's more or less also different like target audience usually. So I don't think you necessarily need to compare them. It's just about what you need in the end, and both can live side by side, where one is built on top of the other, basically.
Okay, nice. Okay, cool. Okay, final question, since I think we still have, is Sam still on the call actually? Yeah, cool. So I
yeah,
think
I'm here.
question is targeted at you. Does the GEE Community Commons replace repositories like Dryad or complement them?
It complements them. It's not designed to replace anything that users are already doing. We are just making it possible for users to basically say, okay, I published something in Dryad, but I also want to create a community catalog request so that data is then transformed. So basically right now, the catalog isn't really serving up just the Dryad links or catalog links to people. We are actually downloading, I'm actually downloading the data, I'm transforming it, tiling it if needed. Sometimes they're netcdf format or some other format. I'm making those transforms, compressing them if needed, and then ingesting them into Google Earth Engine. So there's a pretty large amount of processing that happens in the backend that I'm doing on my weekends. But essentially what I see this as is a way for people to say, okay, I want to store this for archival purposes. I really see Dryad right now as more of a, okay, I'm storing this for archival, but it's not really plug and play ready, versus someone can also then create a request. So imagine like in the future, hopefully if we have time, imagine having a link that says, submit this Dryad data set for community catalog. And then the request comes in as a GitHub request, and we transform that data so that it's available for plug and play. So it's definitely not competing with these services, but it's kind of bringing all of these together and fetching those data sets and making them available for other users to plug and play. And we are also hoping that Dryad and Zenodo and Figshare, advance further in their API capabilities. Right now, it's not very scalable, to say the least. So we're also hoping that this push will also push them in that direction.
Nice. Awesome. Okay, cool. I think I'm going to wrap it up. Thank you so much for joining, especially for everybody who was able to stay late. It's been amazing. I really think that for better or worse, the pandemic has made us Zoom, we're really good at just sticking in there with the Zoom meetings as long as necessary. So yeah, thanks to all our speakers again. That was awesome. And please, if you're interested in these topics, join the cloud computing cluster if you're not already on our mailing list. I think Jim posted the link to our wiki page, which will give you more information about how to join our knowledge sharing sessions moving forward, and also in Slack. And then of course, in a little over 90 minutes, we are going to have the cloud computing tutorials on OpenEO and Dask. So yeah, please join us for that if you can. Thanks, everyone.